Imagine this. It's 3.0 a.m.
Oh, a classic nightmare.
Right. The absolute worst time. You are deploying this critical update for a transaction application, the kind where downtime literally costs, thousands of dollars every single minute.
No pressure at all.
Yeah, exactly. But the new pods are just sitting there. They're totally stuck in a pending state. Your kubectl commands are timing out.
And your heart just sinks.
Yep. And the instinct, the natural reaction is to blame the application code, right? Or maybe the network, or even the Kubernetes API server itself.
Which makes sense on the surface.
It does. But more often than not, the real culprit is this invisible brain of the cluster. It's a component called etc.
Yes. The man behind the curtain.
Exactly. So today we're taking a massive stack of sources. We've got architecture deep dives from dev community, comprehensive management guides from Plural, enterprise administration manuals, and of course, the official Kubernetes documentation itself.
Just really solid stack to pull from.
It is. And our mission for this deep dive is to completely demystify this beating heart of Kubernetes for you.
Because it really is the heart.
It is. Even if you are completely new to this ecosystem, by the end of our conversation, you're going to understand exactly how etc. works, how to keep it healthy, and crucially, how to fix it when it breaks.
Because that 3.0 year AM scenario, it is incredibly common.
Yeah.
Oh, absolutely. So much of Kubernetes' apparent complexity hinges entirely on this one relatively small open source component.
Right.
If you don't understand how it operates under the hood, you'll always be chasing the wrong ghosts during an outage.
Okay, so let's unpack this right from the foundation.
Yeah.
I like to think of etc. as like the ultimate highly organized digital filing cabinet for your entire cluster.
That's a great way to look at it.
The sources describe it as an open source distributed key value store. But if I'm used to something like, a MySQL or a Postgres database,
Yeah, this is going to feel weird.
right, this is a completely different beast, isn't it?
Completely different. If you're used to relational databases with rigid tables, rows, columns, all that, etc., will look a bit alien.
Because it's not tabular at all.
No, it stores data hierarchically,
Hmm.
much like a file system on your laptop.
Okay.
So if Kubernetes needs to find the configuration data for a specific pod, it looks under a key that acts like a file path.
So something like /registry/pod/default.
Slash my pod name. Exactly.
Yeah,
And the value attached to that key is the actual JSON or YAML payload that defines exactly what that pod is supposed to be doing, what image it runs, what resources it needs, all of it.
Okay, and here is where I see a lot of people get tripped up on the architecture, because you might think, well, if it's just a database, I'll just write a script to update the database directly to fix my cluster.
Please don't do that.
Right, because nothing in the cluster is allowed to open that filing cabinet except the Kubernetes API server. It's the absolute exclusive gateway, right?
The API server acts as this incredibly strict bouncer. If every node, every scheduler, and every individual pod could read and write directly to etc., you would have immediate, irreversible race
It's
conditions.
just total chaos.
The system would descend into absolute chaos.
Yeah.
The API server ensures that every single request is authenticated, authorized, and structurally valid before a single byte touches that database.
So it's the gatekeeper.
Totally. It writes your desired state to, etc., and then all the various Kubernetes controllers read from it to make physical reality match that desired state.
Okay, let's pause there, because if it's just this passive digital filing cabinet sitting behind the API server,
Yeah.
why does the whole cluster die if etc. goes offline? I mean, the containers are still physically running on the server racks, right?
Usually, yes.
They have CPU, they have memory. Why panic?
Because without etc., Kubernetes suffers from complete catastrophic amnesia.
Amnesia.
Yeah. Sure, the containers are physically running, but the control plane has completely lost its mind. It doesn't know what it's supposed to be running.
Oh, wow.
It doesn't know where those containers are running or how they should be configured. It loses all tracking of the cluster's state.
So it's literally flying blind.
Exactly. And think about this. If a physical server crashes while etc. is down, Kubernetes has zero memory that the workloads on that server ever existed.
Which means it won't reschedule them.
It will never reschedule them onto a healthy node. Yeah. The API server becomes completely paralyzed because it has nowhere to read from and nowhere to write to.
Which means your 3.00 AM deployment is permanently stuck in limbo until you fix the brain.
Precisely.
Okay, so if it's the brain, it obviously can't afford to have a single point of failure. You can't just run one instance of it on a single server and pray the power never goes out.
That would be a terrible idea.
Right. We have to distribute that memory across multiple nodes. But how does a cluster of separate machines share one unified mind, basically, without getting horribly confused about what the current reality is?
This is where we get into the computer science magic.
I love the magic.
It's so cool. Etc. solves this split brain problem using something called the Raft consensus algorithm.
Oh, fast.
Yeah. In a distributed system, you have multiple servers, and they all need to agree on a single source of truth. Raft achieves this through a strict leader and follower dynamic.
Okay, so someone is in charge.
Right. The nodes essentially hold a continuous election. One etc. node is elected the leader, and the rest become followers.
And the leader is doing the heavy lifting here. If I send an update through Kubexlia, the API server hands it to the leader.
Correct.
But the leader doesn't just quietly save it to its own hard drive and move on.
Not at all. The absolute rule in Raft is that the leader handles all the changes, but it cannot officially commit a change until it proves that the rest of the cluster knows about it.
Proves it.
Yeah. The leader takes your configuration change and replicates it down to all the followers.
Ew.
And then it waits.
It just sits there.
It sits there.
Yeah.
It will not tell the API server the write was successful until a strict majority of the nodes acknowledge that they have safely received and recorded the update.
And that majority is what the sources call a quorum.
Yes, a quorum.
And they actually give us the exact mathematical formula for this, which dictates how we build these clusters. The formula is Q equals the floor of n divided by 2 plus 1,
Right.
where n is the total number of nodes. So let's run the math for you real quick. If you have a 3-node cluster, 3 divided by 2 is 1.5.
And the floor means you just round that down.
Round down to
One.
1. Add 1, and your quorum is 2. You need 2 out of 3 nodes to agree.
Which is exactly why etc. clusters are always deployed in odd numbers, 3, 5, or 7 members.
Wait. Why not even numbers? What if I deployed 4?
If you deploy an even number, say 4 nodes, let's run the math. 4 divided by 2 is 2, plus 1 is 3. Your quorum jumps to 3.
Okay.
So think
Yeah.
about that. In a 3-node cluster, you can survive losing 1 node, right? Because you still have your quorum of 2.
Right.
In a 4-node cluster, you can still only survive losing 1 node before you drop below your new quorum of 3.
Oh, I see.
Yeah, that 4th node gives you 0 extra fault tolerance. It just adds unnecessary network traffic.
So you're just paying for a server that slows you down.
Exactly. A 5-node cluster, however, has a quorum of 3, meaning it can tolerate the loss of 2 full nodes simultaneously and still process transactions perfectly.
Okay, but if I'm building a massive enterprise system, right, like a huge bank, and redundancy is so critical, why stop at 5 or 7 nodes?
I get this question all the time.
Why not run 50 etc. nodes? I want a brain that can survive a meteor strike, wiping out half my data centers.
Because there is a harsh physical limit to consensus, and it all comes down to the speed of light and network cables.
The speed of light.
Literally, increasing the cluster size beyond 5 or 7 members is generally avoided because the network overhead becomes a massive bottleneck.
Because of all the chatting.
Yes. Remember, the Raft rule, the leader has to replicate every single log entry to the followers and wait for that majority acknowledgement. If you have 50 nodes, the network chatter required just to agree on a single tiny pod update is enormous.
Just to say, like, hey, we changed a tag.
Exactly. You aren't making the system safer. You are bogging down the agreement process so heavily that the entire Kubernetes cluster slows to an absolute crawl.
Okay, so we've established that these nodes have to constantly chat with each other over the network to reach this quorum.
Non-stop.
But what happens if there's a network blip or a slow hard drive?
All right.
If they are constantly waiting for an acknowledgement, doesn't a slow connection just freeze the entire API server?
It absolutely does. And this is where most operators look in the wrong direction during an outage.
How so?
When we talk about slow API response times, like when your kubectl commands are lagging or pods are taking forever to schedule, the instinct is to blame the API server.
Right, because it's the thing you're talking to.
Exactly. But the API server is just a stateless proxy.
I actually really like the restaurant analogy for this. I think of it like the API server is the waiter and etc. is the kitchen.
Oh, that's perfect.
Right. You hand your order to the waiter, and the waiter walks back to the kitchen. But if the kitchen is completely overwhelmed and the stoves are barely working, the waiter just stands there waiting for the food.
Just staring at the chef.
Yeah. And to you, sitting out at the table, it looks like you have an incredibly slow, unresponsive waiter. But the root cause is entirely the kitchen.
That analogy perfectly captures the dynamic.
Yeah.
And in the case of etc., the kitchen usually gets bogged down by slow disk I/O.
Disk input output.
Yeah. Raft requires data to be safely written to physical storage before it can be committed. If you are running etc. on slow spinning hard drives or cheap network attached storage, it will bottleneck the entire cluster.
You're basically cooking on a hot plate.
Pretty much. The sources are adamant about this etc. It requires fast NVMe solid-state drives.
Okay, so if you're listening and staring at your Datadog or Grafana dashboard right now, you shouldn't just be looking at CPU usage.
No, CPU is rarely the issue.
What are the specific metrics we need to pull up to catch this before the cluster falls over?
You need to pull up the wall underscore sync underscore duration underscore seconds metric, and also the backend commit durations. If those line charts are spiking, your cluster is about to have a very bad day.
Let's define wall for the listener because it's a critical concept in the sources.
Definitely.
Write-ahead log. Think of wall as a chef writing down the customer's order on a paper ticket before they start cooking.
Right.
If the kitchen suddenly loses power, they can just read the paper tickets when the lights come back on and pick up exactly where they left it.
Yes, and that ticket has to be securely taped to the rail, meaning written to disk, before the chef acknowledges the order.
Oh, I see.
If the physical disk takes too long to acknowledge that the wall entry was saved, the fig duration spikes. The leader can't tell the API server the change is safe, and everything backs up.
Wow. And what about the network side? What metrics warn us that the nodes are struggling to talk to each other?
For network instability, the massive red flag is a metric tracking frequent leader changes.
Meaning the election process is triggering again.
Exactly. If a follower node doesn't hear a heartbeat from the leader in a specific time frame, it assumes the leader is dead and triggers a new election.
So if you see the leadership bouncing around constantly from node to node,
Your network is probably dropping packets. Or the nodes are so CPU-starved they can't process the heartbeats. You should also track the number of proposals, specifically looking at pending, applied, and failed proposals to spot processing delays.
okay, so monitoring health is great. Preventative medicine.
Always the best approach.
But what if a disk literally catches fire during a write? Or, more likely, an administrator accidentally deletes a critical namespace.
The dreaded fat finger mistake.
Right. The data is corrupted. The cluster is essentially dead. We have to talk about disaster recovery.
This is the moment every platform engineer dreads, which is exactly why automated snapshot backups are absolutely mandatory.
But if you are managing it yourself, the sources say engineers must run a tool called accelerate to LL locally on a control plane node just to capture the cluster state.
Yes, and the security around this tool is unforgiving.
I was going to say, to even run the backup command, you have to jump through hoops.
You really do.
Yeah.
You have to provide the CA certificates, the server certificates, and the private keys, which are specifically located in the /etc/ /Kubernetes /pkey/ /etc/ /directory.
That is a mouthful.
It is, and without those cryptographic keys, etc., will flat out refuse to hand over the data.
Okay, so let's say the worst has happened. I have my backup snapshot file, safe and sound.
Okay.
But the live database is totally corrupted. My instinct is to just SSH into the server, forcefully delete the bad file, and copy-paste the backup over the corrupted file to get things running quickly.
Do not do that.
Why is that a terrible idea?
Because if you yank the database out from under an actively running API server that is frantically trying to read and write to it,
Bruh.
you will corrupt the restoration process before it even finishes.
Ouch.
Yeah. There's a very strict order of operations here. You must completely sever the API server's connection first.
But how do you gracefully shut down the API server when the cluster is already malfunctioning?
You have to stop the local kubelet service on the control plane nodes.
Wait, static control plane pods, right? Meaning these pods bypass the normal Kubernetes scheduler?
Exactly right, because the scheduler is currently dead without intention of. The API server doesn't run like a normal application pod. It's a static pod managed directly by the kubelet daemon on that specific physical node.
Got it.
So by stopping the kubelet service, you forcefully take the API server container offline. Once the connection is completely dead, you physically relocate the corrupted etc. data directory out of the way.
Relocate, not delete.
Right. Don't delete it. Move it so you can do forensics later to find out what went wrong.
Smart.
Only then do you run the etc. restore command to unpack the snapshot safely. Finally, you restart the kubelet. It recreates the static control plane pods, and the brain boots back up with the restored memory.
It's basically like inducing a medical coma, performing a brain transplant, and then waking the patient back up.
That is surprisingly accurate. It is intense.
But recovering data is one thing. What if someone is actively trying to steal or poison it? Because that database contains every secret, every API token, every database password for your entire infrastructure, right?
It is the ultimate honeypot.
So how do we lock it down?
The first layer of defense is authentication. We mentioned earlier that the API server is the only component allowed to talk to, etc.
Right, the bouncer.
But how does etc. actually prove it's talking to the API server and not a rogue container pretending to be it?
Good question.
They use MTLS or mutual TLS.
Mutual TLS, meaning it's a two-way street for trust. It's not just the client verifying the server, like when I visit my bank's secure website and my browser checks the bank's certificate.
No, it goes much deeper than that. Both the client, the API server, and the etc. servers cryptographically verify each other's identities using digital certificates before a single byte of data is exchanged.
So if an attacker's pod tries to connect to, etc.
The connection is instantly dropped because the attacker lacks a client certificate that's been cryptographically signed by the cluster's internal certificate authority.
Wow. And we pair that with strict physical network isolation according to the guides.
Absolutely. Etc. nodes should be isolated on a dedicated network segment.
You set rigid firewall rules based on specific ports, like port 2379 is restricted exclusively for client communication, meaning traffic from the API server.
Right.
And port 2380 is restricted for peer-to-peer synchronization, the traffic between the etc. nodes themselves for that raft algorithm we talked about.
Exactly. Everything else is dropped to the firewall.
But we also have to assume a scenario where someone physically walks into the data center and steals the hard drive out of the server rack.
Or an attacker gains root SSH access to the host operating system.
Right, because if they have the physical, etc. database file, network firewalls and MTLS don't really matter anymore.
Nope, they can just read the files.
This is where envelope encryption comes in to protect the data at rest.
A crucial feature.
The sources highlight that Kubernetes encrypts secrets before they are ever written to etc.'s disk. But it uses a wrapped system. It uses a data encryption key, or D, to encrypt the actual secret.
Right.
But then that D is itself wrapped or encrypted by a key encryption key, a keyk. And that keyk is managed securely in a remote key management service, like AWS KMS.
Yes. The reason we use this dual-layer wrapping method all comes down to performance and rotation.
How so?
Encrypting massive amounts of database traffic in real time takes heavy compute power. By using a local, incredibly fast D to encrypt the bulk data, and only using the remote slower key K to encrypt the tiny D itself.
Oh, you save massive amounts of processing time.
Exactly. Plus, if we need to rotate our security keys for compliance, we only have to ask the KMS to rewrap the tiny D.
Rather than spending hours re-encrypting a multi-gigabyte database.
Precisely. It's highly efficient.
The sources note a big difference between KMS version 1 and version 2, though. Why did the industry move away from V1?
Because KMS v1 had a pretty crippling performance impact. Yeah, it required a remote network call over the internet to the cloud provider's KMS to generate a new key for every single individual write operation.
Oh, that sounds incredibly slow.
It was.
Yeah.
KMS v2, which is now the standard, uses a local key derivation function. It generates single-use keys locally based on a master seed.
Which skips the network call.
Exactly. It's exponentially faster and significantly lowers the overhead on the API server.
Okay, so if you are listening to this and feeling a little overwhelmed by the sheer administrative burden of everything we just talked about.
I wouldn't blame you at all.
Right. Calculating Raft node quorums, setting up Datadog alerts for wall-sync disk I/O, rotating MTLS certificates before they expire, and rehearsing strict snapshot restorations.
It's a lot.
You are not alone. It sounds like a full-time job for 5 engineers just to babysit a database. So how do teams actually survive this operational overhead?
By abstracting the chaos.
Abstracting the chaos. I like that.
This is why there is such a massive push toward managed platforms. The sources highlight environments like Amazon EKS, Google GKE, Azure AKS, and specialized infrastructure management platforms like Plural.
Right.
Instead of a platform team manually tracking etc. versions, typing out complex backup commands, and rotating certificates by hand, these platforms automate the entire lifecycle.
We read a lot about Plural in the research. How does a platform like that specifically handle this burden?
Plural uses continuous deployment to constantly reconcile infrastructure states. It essentially acts as an automated operator that ensures etc. is configured to best practices, patched, backed up, and healthy.
Just constantly running in the background.
Yeah. But beyond just the automation, It provides a single pane of glass observability dashboard.
Meaning you can see everything in one place.
Exactly. It integrates the metrics. So
Yep.
instead of jumping between a terminal window for accelerated kill, an AWS console for disk latency, and a logging tool for API server errors.
You're not playing detective across 5 screens.
Right. Everything is correlated for you instantly.
Let's use an analogy here. Running etc. manually is kind of like trying to balance a building's temperature by constantly running around, opening and closing windows, turning radiators on and off yourself.
Exhausting.
Right. A managed platform like Plural is like a smart HVAC system. It constantly measures the room temperature, which is your cluster state, and automatically adjusts the heat and AC to match your desired setting without you ever having to touch a dial or look at a thermometer.
That's spot on, and the value proposition there is enormous.
Because of time saved.
Time and sanity. It frees your engineering team to focus on building the applications that actually generate revenue, rather than spending 30% of their operational time just keeping the cluster's memory from corrupting.
Makes total sense. Let's bring this all together. We started with a mission to demystify the beating heart of Kubernetes, and we've covered a massive amount of ground today.
Really have.
Etc. is the ultimate source of truth, the highly organized filing cabinet holding every configuration for your cluster.
And it relies on the Raft consensus algorithm and a strict odd number quorum to prevent split brain amnesia.
But it demands strict care. You must monitor your wall sync durations to prevent disk bottlenecks, enforce airtight network isolation and MTLS, utilize envelope encryption for data at rest, and maintain rigorous sequenced backup protocols for disaster recovery.
It's a demanding piece of software.
It is, but thankfully all of that can be vastly streamlined with managed automation platforms.
Absolutely.
Understanding these mechanics changes how you will troubleshoot Kubernetes forever.
It's a superpower, honestly.
It is. The next time you get that 3.0 AM alert and you are staring at Datadog wondering why deployment is lagging, you won't just blindly restart the application pod.
Because now you know better.
You will know to check the heartbeat of the cluster itself. You look at the disk metrics. You'll check for RAF leader changes.
You'll check the kitchen, not just the waiter.
Yes, check the kitchen.
This raises an important question, though, and it's a thought to leave you with as you look at the future of infrastructure.
Oh, let's hear it.
As cloud computing pushes toward truly massive scale, we're talking about single managed environments now supporting up to 5,000 nodes and orchestrating millions of AI chips simultaneously.
Mind-boggling scale.
Will the rigid mathematical requirements of the Raft consensus algorithm eventually hit a physical speed limit across global networks?
Wow. It's fascinating to think about. If the network chatter required for 5 or 7 nodes to constantly agree on a state change becomes the ultimate bottleneck for the AI revolution, what will the next evolution of distributed truth even look like?
That physical limit is exactly the problem the next generation of platform engineers will have to solve.
A huge thank you to you for joining us on this deep dive into the brain of Kubernetes. Until next time, keep exploring.